everyone, welcome to the STC training Ocean Forecast System. As the part of coastal hydrodynamics model, I'd like to show you the hydrodynamic simulation model using Delft 3D. First, I'd like to introduce myself. My name is Widya Ayuningtyas. I'm with Mr. Bayu Edo Pratama will accompany you to understand about coastal hydrodynamic model. Now let's start it. Okay, this is the IGF grid window. For the first step is we need to input the land boundaries file. This time I'll use the Indonesia land boundary. Click open. To make grid in Delft 3D, we need land boundary file. And then the output file will be file with GRD extension and ENC extension. Grid file and enclosure file. Now let's zoom to Jakarta area. Then we change the coordinate into spherical coordinate. This one. Next, let's add some splines using the edit menu, click splines and then new. Made spline that on a line with shoreline and upright with the shoreline. I'm just make the half circle shape grid. Make sure that the spline that you made is covering until the land area. Next step, let's change the splines into grids using the operation menu. Click change splines into grid. The grid that we made is not so close to each other. So we need to refine this grid using operation menu, regular grid closeness, then choose refine. Now you have the closer grid. Check the refinement factor of this grid using settings menu, general. This M refinement factor and N refinement factor fill with 3. It means that in M direction, we divided the grid into 3 parts, while the N direction divided into 3 parts too. M direction shows the horizontal axis, while the N direction shows the vertical axis. Refine the grid according to our needs, just like what you want. Next step is orthogonalize the grid. Using operation menu, click orthogonalize grid. Then we need to check the grid orthogonality using view, grid property, click orthogonality, then change the style into the continuous shades. You can see that the red color in the edge shown that the grid hasn't been orthogonalized. for the orthogonality grid, the smaller value is the better. So in the edge of this grid is not being orthogonalized, you need to modify the grid or just click orthogonalize grid until the grid being orthogonal. Next, let's delete the spline using operations. Delete splines. Wait, sorry. Okay. To make the simulation more effective, we need to delete the area that we don't need. There are many areas outside of this domain area. Using edit, regular grid, then block delete exterior. Click on the outside area that you don't need. Then right click. So this area is gone. You can see that there are some grid on the land area. It could make the running simulation not optimal. So we need to use line to land boundary feature. Click edit, regular grid, then line to land boundary. Click on the grid that still in the land area, then right click. Just let's zoom the area. Again, let's start with this one. Now you can see the result. There are no grids on the land area. You can optimize this grid. You can so that the simulation will run faster and more optimal. You can do anything with your grid. This one is far enough from the best grid I've ever made, but let's just move on to the next step. Okay, next step is Quicken. The main purpose of the Quicken program is to create, manipulate, and visualize model bathymetry for the Delft 3D modules, flow, and wipe. Let's get started. First, we need to select working directory. In this case, I'll use the testbathy folder. Then click Quicken. Press the Quicken window. Let's open the land boundary first. I'll use the Jakarta land boundary. Input for the bathymetry is the XYZ file extension. In this model, I'll use the bathymetry data that I get from Batnas. Batnas is Bathymetry Nasional Indonesian website. Open samples and open the bathymetry data. Output bathymetry will be in that file extension, the HD extension if there are any thin dam of the domain area, and dry extension for the dry point area. Dry point area is the area that we don't need to include in the simulation. To make the bathymetry model, we need to define the bathymetry area using polygon. Click Edit, Polygon, New. Make polygon that cover all of the area. For example, Mine will be this one. Now you can see the polygon area that already covered my grid data and the depth data. Make sure that your domain area is covered in this polygon because only the polygon area that will be processed. Now we can do the process in the Quicken. Make sure that you click the data in cell center, this one, and then let's do the grid cell averaging using operation menu. Choose grid cell averaging and wait the process. Next, we click the triangular interpolation. The triangular interpolation will be great to apply to the area which has the smaller density area. Now, let's wait the process. Okay. Next, we can delete sample. You can see that the result of our process before. There are many depth data gone. Do the internal diffusion, click operation, internal diffusion. And then next we delete the polygons. We import, export this file. This one. Close the file. Now we open again the Quicken menu. And then we import the grid file that we made before. Then we import the depth file. Now you can see the depth data on my grid. Let's show the land boundaries. Okay. Now it's good to go. Next step is we need to make the thin dam. You can see on the below, there are many breakwater over here, and we will define that as a thin dam. Now let's try to make thin dam. Click edit and then choose thin dams. You can see that this one is a port and my grid just not as smooth as I expected. So the thin dam will be in this area. Okay. Wait a minute. This area. This small area and then save the thin dams. Choose file. Now after you choose the thin dams, open file. The 3D flow attributes and then click save thin dams. This is just for example. Thin D1. Now let's make the dry point. using the edit menu, click dry point. You can see that there is small island in this area. We define that those island doesn't make any effect to our simulation, so we define that as a dry point. Then save the dry points. I assume that there is only one dry point, okay? So we could move to the next step. Now, I'll explain how to do the flow simulation on Delft 3D. Click Delft 3D until the main menu appears. And first thing first, we need to select working directory. On my case, I'll choose the documents folder and then the tutor Delft 3D folder. Then I'll choose the test flow folder. There it is. Then I'll choose the flow menu. And then we click the flow input. A window will be open. On the description box, let's fill with anything that we want. I'll start with the ocean forecast system training. This time, I'll use the South China Sea as a domain area. And I already made the grid just like the way before. And I choose the grid file and the grid enclosure file. Make sure the coordinate system is spherical. Then click the bathymetry. In this modeling simulation, I already had the bathymetry file and we open the file. Make sure that the bathymetry has value specified at grid cell centers. Then we move to the time frame. In this step, we need to set the simulation start date. In this case, I'll start on January 16, 2019 until January 23 with the time step 5. Now let's move to process. Process menu shows what kind of parameter that we want to calculate in the modeling. For this time, I'll only include wind. Next, on initial conditions. There are 4 options on initial condition: uniform values, initial conditions file, restart file, and map file. For your information, Delft 3D need 3 until 7 days to speed up the model until the model gets stable. So if our running process gets delayed, we can choose restart file as the initial conditions. In this case, because we start from the scratch, let's choose the uniform values as the initial conditions. Next to boundaries menu. In this menu, we describe our boundary condition. For example, in this domain, there are some open boundary and closed boundary. Let's check about the boundary of this domain area with the using view menu and then click visualization area. Now, there are our domain area. We can use the zoom box, this one. This is the open boundaries. This one too is the open boundaries. This is open boundaries also, and this one is open boundaries. Then this one. There are 1, 2, 3, 4, 5, and the small one, 6, 7 open boundaries. Beside that, it only the land boundaries. How we input the M and N value to the boundary zone? First, we need to zoom box the area that we think it's an open boundary. The area belongs to the celibacy. Let's check the M and the N value of this one has 70 and 28. Now we get back to the Delft 3D menu. The celibacy value, input the M and N value just like the information before. The N value start from 128 until 148, which the M value is plus one from the value before, so that we have more space to as an added value. Move to physical parameters. Let's just use default value for gravity, water density, and air density. In the roughness, we choose cheesy. Then we move to the numerical parameters. In this step, you just have to choose the grid cell centers and faces. Make sure the domain menu, make sure this option just has the same option with the symmetry on the domain. Next, move to the operation menu. On this menu, you can add some river discharge data if the domain area has some river. Now we move to monitoring. We can add the observation file. I already have the observation file below. Let's check in the visualization area. For your information, we need to make at least 2 observation area in our simulation model. Now you can see my observation area. The observation area is spot with the blue dot. This one, I just have so many observation area that I need to observe in the simulation flow. Then we move to the additional parameters in this menu. We can add another parameters like pressure, wind velocity, and for this case, I add pressure parameters and the wind velocity parameters, and the name file just like this. Now we move to the output menu. From this data, it's shown that our simulation flowed from January 16 until January 23 with time step 5. In the store map result, you can change the interval based on the way you want to save the simulation. If you need to save every 60 minutes, then fill 60 minutes. Fill the same value to store communication file about the simulation time. Fill 1,440 minutes to restart file to make the simulation save daily. Then save the flow input. Just check this. Okay. Double check the file input again. Make sure that the data on store map result and store communication flow still on the flow simulation time. Okay. Now it's time to run the flow simulation model. Click Start. And choose the test flow file that we saved before. Then click OK. Now the running process is ongoing. Way Delft 3D running. Now the computational program is running process. So just wait. Now we can see that the running process will be finished in 22 seconds. Let's see the result. Just wait for 12 seconds, 10 seconds. Just like it feels like the countdown of New Year's countdown. Okay. Now there are 0 errors, but there are 28. There is too many errors and warnings to write to screen. No, this is about the theme them that I don't describe, but let's just see the result. This is the result of the simulation program. You can see that. Let's check about the error. I guess there are not. No, I guess you can. This is the result of the flow simulation model, and you can see that many warning from this simulation, but there is no error from this model. So I just need to change about the thin dam data from the input flow.